Hello again and welcome to Section 2, Observing the Sky. In this section we're going to discuss things about what do we see in the night sky depending on where we live. Here we have a beautiful example of seeing a lunar eclipse over a cathedral. This was taken in 2017. So moving on. Well, I start off with a just recap of everything we covered in Section 1 again, going back to that universal speed limit, that speed of light. For our purposes, we're just going to call it 3 times 10 to the 8th meters per second. And this is the value that dictates all the properties that we're going to see across the entire universe. Speaking of getting to the universe, when you talk about the scale of things where we exist throughout the universe, and so we say we live on Earth, third rock from the sun. We're one of 8 planets and a couple of dwarf planets and a bunch of asteroids orbiting around our star Sol, and the collective body is called our solar system. And this solar system exists even bigger, the Milky Way, which is about 150,000 light years across. So it takes 150,000 years for light to go from one side of the Milky Way to the other. Going beyond the Milky Way, we would talk about the local cluster. And this is the nearby galaxies. Infamous example is Andromeda is on a collision course with our Milky Way. So we keep getting bigger and bigger in scale. Eventually we get out of the local cluster and we say, well, there's the Laniakea supercluster. And so this is the collection of clusters of galaxies. All right. Coming back to that speed of light, we like to use it to measure time as distances, right? We say a light year, a distance, 9.4 times 10 to the 15th meters. Another time, we'd say a light second. A light second is 3 times 10 to the 8th meters. So we use this time measurement to tell us what is this distance. So once again, to be clear, a light second is a measurement of distance. A light year is a distance measurement. Combine all of our things together, all our observations, we've established that the universe is this 13.7 billion years old. And we'll save discussion of how we got to this number in future sections. But for now, this is an established fact that we understand the universe. And trying to get that established fact, we need things like the cosmological principle. And I'll just repeat it again. Matter and energy obey the same physical laws everywhere. We can go to Mars and expect that we can measure gravity, the same principles. We can shoot photons. We could go to our nearest stellar neighbors, and the physics will work the same there. Now let's talk about what it means for science to be an iterative process. I can pull up the diagram and torture you guys with saying make a hypothesis, do a test, loop around, and let's make it a concrete example. Let's actually talk about what I mean by an iterative process. We'd say we start off with an idea, and I want a concrete example, so I'm going to go with an idea that many of us have heard over the years, and it's this notion that a frog doesn't jump out of boiling water. So there's our idea. Now let's come with a hypothesis. Why? Why does the frog not jump out of the boiling water? And part of our definition of a hypothesis is that it has to be testable. So here's my hypothesis. All right, you put the frog in a cup of cold or lukewarm water, and you slowly bring that water up to a boiling temperature, and the frog doesn't feel any danger, doesn't sense it, so it stays put until you harm the frog or kill it. So this is testable. We could actually do this. So run the experiment. Let's bring a frog to a boil. I'll leave that to the biologists. All right, I'm a physicist. I am not trained in handling frogs properly and safely, and I don't want to accidentally harm these guys. Assuming that we got some friends or we safely did this experiment, what would we find in our results? The frog jumps out, guys. Every time, the frog jumps out. And so we've gone from, I had an idea, we built up an assumption about this, and we tested it. And this is where the amazing power of science is. We can start branching new ideas off of this. We want to repeat our observations. Do we say all frogs jump out? Did I just have my first frog was very wary of temperatures and hopped out anyways, and it's not true for all frogs? Does the rate at which we change the temperature, does that affect this? Does it work for all species of frogs? So we start off with one simple idea, this one idea, and now, even though we've done an experiment, In this case, we rejected our hypothesis. We've branched off into new ideas, new experiments, and that's how science grows. Once we've done all of our experiments, we can finally synthesize everything into our scientific theories. And scientific theories isn't like the Sherlock Holmes theory, I have a hunch of what's going on. These theories are the culmination of years of hard evidence, hard work. Multiple people have collaborated this, and the world as a scientific community has decided, yes, these principles hold true, and it allows us to make future predictions to try and better understand the world. So things like gravity, evolution, as an example of seeing a crocoduck. Relativity, an extension of our understanding of gravity. These are all ideas that we've tested thoroughly. And the biggest rule that scientists want to use is this Occam's razor, which just boils down to, hey, if we have different ideas, I have different hypotheses, we prefer the one that requires the fewest number of assumptions, the one that requires the fewest amount of input, basically.